Hi, my name is Jonathan Chu. I'm the National Content Director of High School Programs for the Princeton Review. Today what we're going to do is look at some of the problems that were released by the College Board for the redesigned SAT. In this particular problem, we're investigating what would be the mass of a metal hexagonal nut that has sides of lengths 2, a thickness of 1, and a hole with a diameter of 2 is drilled through the center of this nut. And so the first question that might pop into your mind is, well, where in the heck do I begin? Right? So for Princeton Review students, they're coached to think about problems in stepwise fashion. So they're going to break this problem up into bite-sized pieces. And by doing so, we're going to systematically attack this problem by solving for one thing at a time in a logical fashion that will make sense to get us down to the final answer. And so the first thing we would do here is actually label all the information that is given to us in the problem. So in this metal hexagonal nut, we know that we have a thickness of 1, and this has sides of lengths of 2, and this hole in the middle has a diameter also of 2. The problem tells us that the density is equal to 7.9. But you might ask yourself, well, how in the heck am I supposed to find the mass of an object when given the density? And notice how the problem actually gives us that formula at the end of the problem. That the density of an object is equal to the mass divided by the volume. So, according to our methodologies, we will always write the complete formula down because when you do, it lets you identify what you can plug in and what we need to solve. We know that the density of this figure is 7.9. We're trying to find the mass. So therefore, somehow, some way, through the information given to us in the problem, we will be able to find the volume of this object. All right, so now this is going to be the key. We didn't know we had to find the volume at first, but once we wrote this formula down, we were able to identify that. So how are we supposed to find the volume of an object in which there is a hole that is actually drilled through it as well? And so there are two ways that we can actually do this. The first way is to actually solve for the volume directly of this shape that has an irregular shape because a part of it is missing. So that's going to be a little bit more difficult. So the second way that we can solve for the volume of this object is to imagine that this hole were filled. And so therefore, if we solve for the volume of the entire metal nut, and then subtracted out the volume of the shape that was drilled into this, we would then be able to get the volume of the resulting object. So let's go ahead and do that. But in order to do so, we would have to kind of figure out how do you find the volume of a metal hexagonal nut. And so let's actually take into account a rectangular solid. In a rectangular solid, if we think in geometry so far, we know that the volume of this object is equal to length times width times height. But why is that? Right? Let's investigate this. So the volume of this would be length times width times height, and that is because the length and the width make up the area of the base. So if you imagine that this rectangular box is just a sheet of paper for the base, and you stacked multiple sheets of paper on top of each other, you would in essence create a box. Right? So the height, however many layers of sheets of paper you have, you would get an increasing height, and the resulting shape would get increasing volume. So if I can figure out the area of the base of a figure, and know that if I stacked all those areas on top of each other to get a height, I would be able to solve for the volume of that object. So in breaking this down, if I flip this metal hexagonal nut onto its base, I would essentially get a hexagon. A hexagon that has sides all of lengths 2 because the problem said that this was a regular hexagon. And that would mean that all the sides of the hexagon are congruent. So once we know that the sides here are 2, we would then have to figure out, well, how do I know what the area of a hexagon is? That may not be one of the formulas that are just going to resonate in our minds. But what we can do, and part of our Princeton Review methodology here, is to break down complex shapes into known shapes. And when we do that, we would be able to break this hexagon down into 6 congruent triangles, and I would know also that these are going to be hexagonal, these are going to be equilateral triangles, and they're equilateral because all the sides of the triangle are equal to each other. And so therefore, if I do know that the area of this triangle would be one equilateral triangle, if I can find the area of that and multiply it out by 6, I would then in essence be able to get the area of the entire figure. So what would be the area of the equilateral triangle? Well, the area of any triangle is going to be 1/2 base times height. And we can certainly do that by breaking down this equilateral triangle further. But if we know that that the area of an equilateral triangle, that's actually going to be equal to s squared times radical 3 over 4, this special area formula applies only to equilateral triangles. And this is advantageous to us because we would only need to know the side, the value of the side of the equilateral triangle. So when we plug that into our formula, we would get 2 squared times radical 3 over 4. So the area of an equilateral triangle would be equal to radical 3. That's just the area for one of these triangles. So therefore, I would multiply that value by 6. So the area of the hexagon would be equal to 6 radical 3. So now that we've solved for the area of the base, kind of like what we did down here, right? We got the area. Now we just have to figure out how many of these there are, and that would be the height. The height of this would correspond to 1. So therefore, the volume of the hexagon will be equal to 6 radical 3 times 1, which is equal to 6 root 3. So now we have solved for the volume of this metal hexagonal nut if there were no hole drilled through the middle. But now if we are able to solve for the volume of that cylinder that's drilled, or that hole in the middle of this metal nut, we would be able to then subtract that out from the value that we've just calculated. So how do we actually do that? If you can imagine that the hole that is drilled in the middle, if you look through it, it would be a cylinder. And so therefore, the volume of a cylinder is equal to pi times r squared h. The radius, because the diameter is 2, the radius would be 1, and the height would again be 1 as well, because this has a thickness of 1. So the volume of the cylinder here would be equal to pi, so therefore the volume of the hexagonal metal nut with a hole drilled in the middle will be equal to 6 root 3 minus this pi, which gives us approximately 7.25. So we've systematically now used the areas from equilateral triangles, moving on to the volume of this metal nut, found the volume of the cylinder, and now we found the volume of the 7.25. And we might now forget, why do we even go this route in the first place? And this is exactly why we always write the full formulas down, because now that I know the volume is 7.25, I can complete this formula over here. So 7.9 is equal to the mass over the volume of 7.25. So therefore, multiplying both sides by 7.25, I then get that the mass is equal to around 57. Does that answer the question? The question asks us for the mass of the nut. We have solved for the mass of the nut, and so therefore, we have the right answer. There are a lot of steps here, but what we did was we used bite-sized pieces. We followed good Princeton Review systematic methodology. There were a lot of steps, but they logically followed each other. There was a story to be told, and so therefore, once we, again, follow the formulas, found those values, plugged them into our master equation on this side, we got the right answer. We know we got the right answer as long as our math is correct, and we can move on to the next question.